Hi everybody, welcome to another video in Calculus, section 6.4, Trigonometry Identities. So an identity is an equation that is true for every values of the variable. So for example, we have this equation f of x equal to g of x for every values of x. In this case, we say that equation is an identity, or we say that it is identically equal to each other. Right. An equation like this, if it is only true for some values of x, it is called a conditional equation. Conditional equation meaning that it is true for some values of x. Right. Here are the identities that we learned before. This in chapter 5 we have exactly this and the hexagon. So quickly, we have reciprocal identities, meaning that cosecant is reciprocal of sine, cosine and secant are reciprocal of each other, tangent and cotangent are reciprocal of each other. And we also have the quotient, tangent equal to sine over cosine or secant over cosecant. And because tangent is also 1 over cotangent. So we have a function on top, there will be 3 ratio. This, the quotient identities, and the other one opposite to that is reciprocal identity. So we can rotate any function on the top. For example, if we put cosine on the top, cosine will be equal to cotangent over cosecant, sine over tangent, and 1 over secant. Right. Next we have Pythagorean identities. Cosine square plus sine square is 1, 1 square plus tangent square, secant square, and cotangent square plus 1 square is cosecant square. So we go in that direction. We also have even and odd identities. This function sine, cosecant, tangent, and cotangent, these are odd function, and odd function by definition f of negative x is equal to negative f of x. The other two functions, namely cosine and secant, are even, and even function f of negative x equal to f of x. Right, so these are the identities that we know, the basic identities. Now we're going to use that to prove some other identities. Right, so the way we prove an identity, first the technique. We can rewrite the expression in terms of sine, cosine, so that might help. I will use this a lot. So express in terms of sine, cosine, because when we have sine, cosine, it's easy to see where they combine. And one identity that we use a few times is just cosine square plus sine square equal to 1. So when we write everything in terms of sine, cosine, then we only have that identity instead of the other two. So it's less thing to worry about. So at the more basic level, we should keep testing in sine, cosine. That might help us to get things started. Right. Or we can multiply the numerator or the denominator by the ratio that is a well-chosen one. By that, I mean we not multiply by 1. What we actually multiply by is something, the same thing on the top, the same thing at the bottom. If we have the same thing on the top, the same thing at the bottom, that reduces to 1, right? So the well-chosen one is meaning that we multiply something on the top and the same thing at the bottom. And it will help us to simplify the problem. or we can write the sum of trigonometric ratio as a single ratio. So like we add two fractions with the common denominators, and finally we can also factor. Right, so those are the techniques that we can use. So we write sine, cosine, multiply the same thing top and bottom, combine using the common denominator, and then factor. But the sine cosine thing, first time I use in more than one occasion. Right, some guidelines. Usually when we try to prove, we might work for the more complicated sign and just simplify it. We can rewrite them as the single quotient, like common denominators. So, and then sometimes it helps if we write in terms of sine, cosine. That's of course something we already mentioned before. And the last one is nice. When we're trying to prove something, usually we have the left side and the right side, so we know if we start from one side, we can go to the other side. So make sure that we try to get to that side. We just don't do any random manipulation and hope that it will work. Of course, we have to have a way to go from one side to the other. Right. Now, if it is difficult to go from one side to the other, there's a less common way, but still work, is try to prove equivalent identity. Right. Now, before we actually prove any identities, just want to go over, just trying to simplify something like this. Right, tangent over secant. By the way, is that an identity already? So let's look at the hexagon again. If we have tangent over secant, well, if we put tangent over secant, then we have sine on the top. So therefore, tangent over secant is equal to sine. But is that equal to sine? Well, let's first rule is if you want trying to simplify things a little, try just put everything in terms of sine, cosine. Tangent is sine over cosine. Secant is 1 over cosine. Now, divide fraction is multiply reciprocal. So just simplify, and we have sine over 1 is equal to sine. Right, simple enough. Well, the next one, let's see what we can do. Right, there's tangent in sine, there's cosine. So might help, why don't we just write everything in terms of sine, cosine. Well, might not be the best, but it's not wrong. Right, I'll keep cosine square on the top. At the bottom, I will have sine over cosine times cosine, and then tangent is sine over cosine. What we can simplify here, we see is more often than not when we have cosine square or sine square, we might use Pythagorean identity. Actually, there might be something else, but I just look at Pythagorean identity first. Cosine square plus sine square is equal to 1. Subtract 1 on both sides and subtract sine square on both sides. We have cosine square minus 1 equal minus sine square. Right, so cosine square minus 1 is minus sine square. So I use that for this and they have negative sine square. Right at the bottom, what can we do here? Well, of course, we can simplify the cosine here, right? That certainly works. However, what we see here is that both of them have the cosine at the bottom. So we, to our advantage, just to keep the cosine here, multiply cosine here on the top. So we have both of them have cosine at the bottom. Right, now I can combine the denominator, right? So I have sine, cosine, plus sine, all of that over the denominator of cosine theta. The big fraction, the top will be negative sine square. Right. I can factor out the sine of theta. So I have cosine of theta plus 1 over cosine of theta. Right. Divide fraction. Notice this is a big fraction here. Multiply reciprocal. Cosine at the top, sine at the bottom. Cosine theta plus 1. Right. We can cancel one sine at the bottom and that. So we end up with negative sine and cosine over cosine theta plus 1. Right. Can we simplify it further? Probably not, but just something lateral. Right. So when we simplify things, of course, we can end up being a lot of different things. But when we prove an identity, we know exactly what we end up with. Right. Now I could try something else here. So I still write cosine square on the top, minus 1. The bottom is tangent of theta, cosine of theta, plus tangent of theta. Right. Now, if the bottom, I will write the same thing, right? Expand and sine cosine, combine the top with common denominator. So I have sine and cosine plus 1 over cosine. Now, the cosine square minus 1. Instead of writing that as a negative sine square, I could write as a difference of 2 square. So we use that instead. And we will have cosine minus 1, cosine plus 1, and over sine, cosine plus 1 over cosine. Now, multiply reciprocal. Sorry, just have the top, we just have cosine theta plus 1. Now multiply reciprocal, cosine theta, sine, and cosine theta plus 1. And we have the cosine theta plus 1 cancel with this one, and we end up with cosine theta minus 1 times cosine, sorry about that, I have space here, over sine. So we have that, or this, are they the same? Well, actually they are the same, as you see in the next example. But now if we don't know if they are the same, of course this is not a proof, but at least we can do the quick check. Of course, if it's not the same, then we can see it right away. But if it is the same, then we have to do some other work. But here's a way to check it. First, make sure that it is in the radian mode when we do this. I put two functions, negative sine x, cosine x, divided by cosine x plus 1. And then the second function is cosine theta, cosine x minus 1 times cosine x divided by sine of x. And you hit graph, of course. Hit graph and then to say, how do we confirm that? Right. Now, of course, if the graph two identical graph, then difficult to see. But the way to check this is we keep the first graph, the second graph. Now go click the arrow, go to the left, and hit enter a few times until we see that pattern. I mean this pattern with the circle. Now we see if we graph the first graph, you see the dot. That is when it plot the second graph, it will trace on the top of the first graph. So at least you can see that at least they have the identical graph. Well, like I said, if we have to prove that they are equal, we have to do some extra work, and we're going to do that in a minute. Now, by the way, those are kind of the lateral move, because it doesn't look like one is more simplified than the other. But now, I just want you to pay attention to this. We have sine, oh wait, sorry. I mean, including the negative sine over cosine plus 1. Compare that with this. Both of them, if you ignore the cosine, I mean cancel cosine both sides, then you have cosine minus 1 over sine is equal to negative sine over cosine plus 1. Of course, that should be the case, because we do prove this. Now, if you have the negative, move this negative to the other side, it will become this. So pretty much, when we prove this, we show that these two are equal. But like I said, it will be difficult to usually try to simplify the trigonometric identities, unless it is equal to something obvious like this. When we have something like this, we cannot simplify it further, and it's difficult to, I mean, possible to tell which one is more simplified than the other. So if it is complicated like that, we just stop there. Right, now this we actually prove something like this. I'm going to prove this in, let's say, 3 different ways. Right, actually in this, I mean, not counting the graph is not a proof, so maybe 2 or 3. Right, now notice that if we're going to write this, of course this is not a proof. I repeat, this is not a proof. Let's just try to cross multiply. Sine times sine and we have 1 minus sine, 1 minus cosine times 1 plus cosine give a sine square 1 times 1, and then cosine theta minus cosine theta and minus cosine square. Because cosine square minus cosine square cancel out the middle term, because that we can also use the difference of two square. I give a sine square equal to 1 minus cosine square, right? And then of course we add cosine square on both sides. So we know this is true and every one of them is true, and then you say, why that's not a proof? None of this operation is wrong. Of course, none of those operations are wrong, but usually in the spirit of proving something, we don't know that is true or not. But what we can do is, like I said, this is not a proof. But if we want to use this as a proof, all we need to do is just write things backward. Now, I will use this in two different proofs. So one way of the proof is trying to prove equivalent identities. So now I just write this in reverse. So first, everybody knows that sine square plus cosine square is 1. We know this one is true. So we can move the cosine square on the other side. And 1 minus cosine square, difference of two square, I can write as right. The sine square, why don't we write sine times sine? And finally, just scramble. Move the 1 minus cosine to this side and move the sine to the other. So, like I said, we cannot start from this and cross multiply. Usually cross multiply it doesn't work like that, because what we cannot use this is that we cannot assume that something we're going to prove is true. Usually the proof doesn't start with that. The proof is better to establish from something is already true, and we manipulate that to something else. And since all of these are equivalent to each other, if the first one is true, the last one is also true. So that's a proof of this. Now, another proof is sometimes we go from one side to the other, right? Now we're going to do that too, which is more common. So let's see, alternatively. Now, usually when we prove, you see this quite common. So let's start with the left side, and to simplify that to the right hand side, because they both equally complicated. So we don't know where we start with. So let's just go from left side to the right side. Sine 1 minus cosine. Right. Now, remember one of the guidelines that we have on the previous page saying when we're trying to prove from one side to the other, keep in mind, if it doesn't seem like we're going to simplify to something, because like I said, they're equally complicated. So we cannot really simplify from one side to the other. Just try to somehow get to the other side. So in order to get to the other side, we can do two things. First, multiply sign on the top and the bottom, so that we have the sign at the bottom. But that doesn't really help, because it doesn't look like it can cancel anything. So we could multiply by the well-chosen one. So we multiply something top and bottom, the same thing on the top and bottom. Right. So here look like we have 1 plus cosine on the top. So why don't we do that? Times 1 plus cosine on the top and 1 plus cosine at the bottom. Now this is of course equal to 1, and that's why they said multiply by a well-chosen one, meaning the same thing on the top as the bottom. Right, now multiply it out. I'll just multiply the top and then at the bottom 1 minus cosine times 1 plus cosine. And we did say that these are different of two squares. One square minus 1, because you can write 1 square too if you want to. Different of two squares. And on the top, don't do anything. Now, we have sine and 1 plus cosine of theta. Okay, now if we're going to write 1 square cosine square equal to this, then we go backwards. So we have to try something else rather than going backwards. What we have is that, of course, is similar to what we have here, Pythagorean identity, where we have a square. So cosine square plus sine square is equal to 1. And so let me write that here. Okay. Cosine square plus sine square is equal to 1. Now here we have 1 minus cosine square, so I minus cosine square on both sides. So sine square equal to 1 minus cosine square. So we have this at the bottom, which is equal to sine square. And cancel one of the sine on the top with one at the bottom. We end up with 1 plus cosine of theta over sine of theta. And that equal to the right hand side. Right. So you see, this is more a standard proof. We'll go to from one side to the other. This is less conventional, but it also works. Right. So if we can go from one side to the other, that is the preferred way to prove. And when we don't know from one side to the other, try to manipulate that. If we end up with an identity which is good, write everything in reverse and you have to prove. Right. Now this one is obvious. We know that this side is more complicated than this side. So in that case, why don't we just try to simplify the left hand side, make sure that is equal to the right hand side. Right. So the left hand side equal to 1 plus sine 1 plus cosecant so 1 plus sine. And now It will help if we write everything in terms of sine and cosine, right? So 1 minus cosine, cosecant is 1 over cosine. Right, so I have that help. Right. So here, of course, we can multiply the common denominator and then try to combine them. But what I'm trying to do here is simplify a fraction. So try to simplify. Sorry. Cosecant is 1 over sine. Right. Sorry. Right. So what I'm trying to do is trying to simplify the fraction. By that, to multiply something top and bottom. So look like this is a fraction. If I multiply sine at the bottom, it will cancel with this sign, which is good. Multiply sine at the top. Right. So I'll just keep 1 plus sine times sine. I don't multiply it out yet. You know why I don't multiply it out? Because at the bottom, at the end result is equal to sine. So always pay attention to what we end up with. We have sine at the bottom, so we might want to keep this term because this might cancel out nicely. So try to keep that in mind. That's why I won't multiply it out yet, because at the end there should be a sine, and that's what we have. Now, sine times 1 is sine. And sine cancel out. We have 1. Sine times sine equal to 1. Sine cancel out. Now as you see, we have sine plus 1 on the top, cosine. Those two cancel out. And we have sine of theta. Right? So even though we can multiply it out, but don't. Because we look at the end, have the sine theta by itself, so we might want to keep that term there. So we will cancel. Right. Of course, there's another way to do this is you can write this over 1 and then cross multiply. Let's see if we can do that. Another way to do this is write that over 1 and cross multiply. Cross multiply, we have 1 times 1 is 1. Sine times 1 is sine theta. The other side is 1 plus cosecant theta times sine of theta. Now 1 plus sine theta. Cosecant is 1 over sine theta. Sine theta. Multiply it out, sine theta, and sine out is 1. Now because they are equal, so it's proof. Like I said, it's not like this. All we do is we just write everything in reverse, from here to there, and finally back to that. But like I said, if we have an equation, an identities, which one side is a lot more complicated than the other, just try to start with the more complicated side and simplify it. Right. Let's look at this example. Right. Once again, it's obvious that the left-hand side is more complicated, so let's start with that. Sine 1 plus cosine theta 1 plus cosine theta sine. Well, we have cosecant on the other side. Not sure how we get that, but what we can do is look like if we want to combine the fraction, we need a common denominator. So try to simplify it first. Of course, I don't know how to get to cosecant yet, but at least we can combine them. We need a common denominator to multiply them, right? So I'm multiplying same thing top and bottom. So the common denominator is sine times 1 plus cosine. So I multiply sine on the top, sine at the bottom here. And then on the other one, 1 plus cosine and sine. I'll multiply by the 1 plus cosine. So I have the common denominator. And the top, of course, have to be the same thing. Sorry, the program is frozen for some second. Stop recording. Right, so what we have is the common denominator of sine and sine times 1 plus cosine at the bottom. On the top we have sine times sine, give us sine square. And multiply this. These are not different to square, so we're just going to multiply it out. 1 times 1, 1 times cosine, cosine times 1, and cosine square. Right, so as I mentioned before, usually when we have sine square and cosine square plus sine square, that difference is 1, right? So when we have sine square or cosine square, the identity, the Pythagorean identity may be useful there. Right? So cosine square plus sine square is 1. 1 plus 1, make that 2. But we do that later. We still have 1 cosine plus cosine is 2 cosine. Right, we have sine 1 plus cosine theta. Right. Again, we don't know how to get to cosecant yet, but at least we have a 2. Right. Now, a 1 plus 1 equals 2. Right. Now it should be clear from now. Of course, cosecant is 1 over sine. We do have sine at the bottom, which is good too. Now both of them have a 2, so I will factor out the 2. So I have 1 plus cosine theta, and then sine, and 1 plus cosine theta. Cancel out that. We have 2 over sine, which is secant. If we have sine at the bottom, that's secant. I mean cosecant, sorry. And that was equal to the right hand side. Right. So that's the proof of that problem. Yeah, I'm drawing this problem. I'm not going to try to cross multiply and simplify that to something equivalent, because obviously in this problem we should simplify from the more complicated side to the other side. Same thing here. I'm not going to cross multiply anything, just trying to go from this side to the other side. So the more complicated side is the left hand side here. Tangent plus cotangent. Well, I just write the problem first. secant, cosecant. Now, tangent, you can rewrite that as the ratio sine over cosine, and cotangent is cosine over sine. Yeah, I try to write everything in terms of sine, cosine. Secant 1 over sine, 1 over cosine, sorry, and cosecant is 1 over sine. Now what we see here is the denominator for the fraction, the bottom has cosine over cosine and sine, and the common denominator of the top is cosine and sine. So why don't we multiply top and bottom by sine, cosine. So when we do that, common denominator, we simplify something. Right, let's see. We have sine times cosine. Sine times cosine multiply to this. Cosine cancel out. We have sine times sine on the top for the first term, right? And then when we multiply this together, sine on the bottom and sine on the top, we have cosine times cosine, which is cosine squared, which is equals 1. And then sine cancel cosine, cosine cancel cosine, so we have this. Sine squared plus cosine squared because it's 1. Right, so that's how we prove. Usually we work from more complicated sign, go to the other. Of course, when we have something that look like equally complicated, we can just manipulate them, cross multiply, and then write everything in reverse. Or we can just go from one side to the other. And keep in mind what we're trying to get to the other side. Right. There are a lot of things we can do, but that's all the samples I want to cover in this section. As always, thank you for watching, and see you in another video in calculus.